This is section 9.7, Applications of Right Triangles. Before we get into the topic of applying our trigonometry to right triangle problems, I want to talk a little bit about significant digits, because in this particular section they want you to use a correct number of significant digits, which is different from what I've been saying. And so we're going to practice this in this particular section. Whereas I've said I'd like your answer to be correct to 3 numbers after the decimal point, they want you in this section to practice using significant digits. So still typically what I'm going to want is 3 decimal places. If they say in the directions use significant digits, then I want to make sure that you know how to do that correctly. Since almost everything that we find with trigonometric functions will be an approximation, because there are a few answers which are nice rational numbers, but most of them are irrational. And therefore, if you want to record the answer as a decimal, you're going to have to round. And so this significant digits idea becomes very important. So to practice, I'd like for you to look at these numbers and make a decision as to how many significant digits there are. And if you get them wrong, we need to talk about them together. But I would like for you to try these all on your own first. Or maybe, one at a time, pause and replay and pause and replay if you want to slow it down so that you have a chance to correct any mistakes you're making and see if you get it right later. So pause and we'll get the number of significant digits on these particular numbers. Okay, so how many significant figures or significant digits does the first number have? Well, that's 3. How about the next one? That's 4. Trailing zeros after the decimal point, zeros at the end of a decimal number are always significant. So there are 4 significant digits there. Those 2 zeros are significant. How about the next one? Right, that's 4, according to the discussion we just had about trailing zeros after the decimal point. Okay, how about the next one? Well, that one only has 2 significant digits. The zeros between the decimal point and the first non-zero number between the decimal point and 3, those are not significant, and the 0 in front of the decimal point is not significant by itself. So those zeros in the tenths and hundredths place are simply placeholders and are not considered significant. Okay, try the next one. It has 4. The 0 in front of the 3 is not significant, but the trailing 0 at the end after the 6 is. So 3, 1, 6, and 0 are all significant. How about the next one? There are 2. Again, kind of like the 4th one over there, those zeros between the non-zero number and the decimal point, which we could put a decimal point there if we wanted to, those zeros between the 8 and the decimal point are not significant. They're placeholders, just like the 0, 0 in the 0.0036. Those zeros are placeholders. So there are only 2 significant digits in that particular number. I will say that if you can write an exact answer like square root of 3 over 2, that's always preferred. The only time that you back off from that is if you're asked for a decimal approximation, then you give that. But if you can write the exact answer, that's preferable. Pi over 6 is way better than the decimal form of it. Okay, so in this particular section, I just mentioned pi over 6. It's not going to be used in this particular section. In these triangle problems, every angle will be measured in degrees. So for this section, kind of put radians to the back burner and don't forget about them, but they're not going to be used in this section. All right. So let's do some examples. The first one says solve the right triangle ABC with A equal to 34 degrees, 30 minutes, and C is equal to 12.7 inches, round using significant digits. Okay, so that trumps my 3 decimal places rule because directions always supersede anything I might say as a general rule, like number of decimal places. Okay, so 34 degrees, 30 minutes, has 3 significant digits. That last 0 is not significant, placeholder. And that's angle A. As I said earlier, in a right triangle, unless they say otherwise, if it's called ABC, almost always the right angle is C. And we'll make that assumption until they tell us otherwise. So that means that this is side A, this is side C, and this is side B. The side across from the angle gives it its name, and the sides are in lowercase letters, the angle's in uppercase. All right, and they tell us that C is 12.7 inches. It too has 3 significant digits, so our answer will have 3 significant digits. All right, so to solve a right triangle, what that means is when you're done, you should know all 3 angles and all 3 sides. That's what solving a right triangle means, or solving a triangle in general. Means knowing all 3 angles and all 3 sides by the time you're done. Okay, so because angle C is our 90-degree angle, so it was our assumption, how will we find angle B? Well, we can use the fact that in a right triangle, or in fact in any triangle, the 3 angles add up to be 180 degrees, and in a right triangle, if one of them is 90 degrees, it means that A and B in this problem have to be complementary. So you can do one of 2 things here. You can say, well, the sum of all 3 is 180. So B will be 180 minus the 2 that you know, which is generally going to be true for us. We're going to use this one a lot. But because it's a right triangle, we could have said that B, because it's the complement of A, is going to be 90 degrees minus the measure of A. And you see that thought process, although slightly different, if you combine the like terms here, 180 minus 90, you're going to get that same 90. So it's not going to give you a different answer, of course. It's just kind of a different thought process to get you there. All right, so if you subtract 90 degrees minus 34 degrees, 30 minutes, you should get, if you'll recall, you'll want to borrow 1 degree and call that 60 minutes. So 90 degrees is the same thing as 89 degrees, 60 minutes, minus 34 degrees, 30 minutes. And so B is 55 degrees, 30 minutes. Notice how I'm labeling everything I'm doing. C equals, B equals. I'm going to look for that so that I know what your answer is, and the label, since there are lots of answers in this particular problem, tells me that that's specifically angle B that you're finding, and I need for you to label every answer. So notice C equals 90 degrees is labeled with C equals. And don't forget the units are degrees, and then B, it's actually minutes as well. So make sure that you have that unit measurement is in degrees, so make sure that that's true. All right, so since this is a right triangle, that means that our right triangle definitions of the trig functions are valid. And we could say, for example, that the sine of the angle that we were given, besides the angle C, which is a right angle, but we can say that the sine of the given angle A is opposite A over hypotenuse, which is c, and we were told what c is. And if we can write an equation that's true, where only one thing is unknown, like the side A here is unknown, we can solve for A. So to solve for A, we'll want to multiply both sides of the equation by 12.7. And then this is what I call calculator ready form. It's ready to just type in your calculator and record the answer. I'm, for the most part, going to just give you these answers. You should probably pause the recording and type every time in that's something kind of new, a little bit different. At least then you should try to get every single keystroke practiced so that when you do this on a test or something, you're not wondering how to type things in your calculator. So you should get 7.19. And that's using 3 significant digits, by the way. I rounded to 7.19, 3 significant digits. Now, are we done with A? Oh, not quite. You have to look for the units of measure. And A, since it's a side length, will be in inches. So make sure you don't forget your units in the answer for the side length. Okay, so the only missing piece of information is side B. And think about what trig function you could use that would relate side B to the known side. Now, I could very well say that would relate A, which we just calculated, to B. The problem is if you retype 7.9, that's actually erroneous. It's not correct exactly. We rounded to get that number. And so what I'm going to ask that you always do is try to, as much as you can, to avoid using a calculated number to calculate something else. If you can find the correct answer using only givens, that's what I want you to do. So angle A is given, side C is given, B is what we want. What trig function relates adjacent and hypotenuse to an angle? Well, that's cosine. So the cosine of 34 degrees, 30 minutes, should be equal to adjacent, which is unknown B, divided by hypotenuse, which is known to be 12.7. Oops, a little stray mark there. Let me get rid of that, if I can. There we go. Then to solve for B, multiply both sides by 12.7. And there's the calculator ready form. You might notice that it's very similar to the problem we did a few seconds ago. The typing of it shouldn't be any harder because you're just typing a cosine instead of a sine, but please make sure you're at least occasionally pausing. Oops. But you're at least occasionally pausing and typing some of these in for practice, because you'll know what the correct answer is supposed to be. Okay, so for this one, using 3 significant digits, the answer you get should be 10.5. And are we done? Oh, yeah, we have to write the units, and that would be in inches. All right, so that finishes our first example. All right, let's do another example. Solve right triangle ABC if, let me draw a triangle here. I always like to draw a picture because it gets my relationships, what's adjacent, what's opposite, what's hypotenuse, and all that good stuff. I like to be able to see it to make sure that I'm creating things correctly. So again, we're going to make an assumption that C is the 90-degree angle, unless they tell us otherwise. In a triangle ABC, we'll generally call C the right angle, and the one that you label A or B doesn't matter as far as which angle is which. If you're trying to make it look to scale, it might make a bit of a difference, but if you're just trying to make sure you have relationships correct, I'm not too worried about your triangle, whether it's drawn perfectly or not. All right, so they tell us that A is 29.43 centimeters. And they tell us that C is 53.58. centimeters. Now the 90 degrees that I wrote, I introduced that. I know it only has one significant digit, but that's something I introduced as an answer. Look at the givens. We have 4 significant digits. So the rounding using significant digits, just keep in mind that you're wanting to use 4 significant digits for this problem. Okay, so it's our choice what we decide to go for next. We have side A and C. C, of course, is the hypotenuse. So if I choose A will be opposite. If I choose B, A will be adjacent. So it really doesn't matter which of those you decide to do. Why not go with B? So if it's adjacent and hypotenuse, cosine is the thing that relates those 2 sides to the angle B. So the cosine of B will be adjacent, which is the 29.43, divided by hypotenuse, which is 53.58. And then to get B by itself, that's where we use that inverse cosine we talked about previously. Make sure that you're in degree mode, because you are solving a right triangle, which we're going to assume always uses degrees for right triangle type problems. And so that's a new thing. So I would pause the recording right now and type that in my calculator to make sure that I get the right answer, and don't forget your rounding rules. Okay, you should have gotten 56.68 degrees. So how are we going to find A? Well, if you're going to find A using the fact that they add up to 180, you're going to be introducing the 56.68 number into that calculation, and that's a bit risky. So if you decide you have to do it that way, and there's some problems where you cannot avoid using a calculated number to go forward, I want to show you or talk to you about how to do this on your calculator. And in your calculator, you're going to have to figure out where these buttons are and what it looks like, because there are many calculators out there made by different companies, and they have different buttons and different ways of doing this. So you might have to actually Google the name of your calculator and ask it how to store numbers in memory, or how to use memory, and then how to recall those numbers. So what I'm going to suggest you do is, let's just pretend like we can't find A except by using the angle B we've already calculated, because I want you to practice this before you have to be able to do it. Because if I were going to find A the straight up way without using anything but what I already know, I would realize that the sine of A is opposite over hypotenuse. And that's what I would use with sine inverse, and I'd get an answer. In fact, we might let this one be done twice as sort of a check on what we got. What I'm writing right now is what I would want you to do, because you're not forced to use angle B to find angle A, because this is an option. So this would be what I would want you to do for sure. And so that would get your correct answer of, let's see, A is 33.32 degrees. Let's talk about the storing. So what I would ask for you to do for practice, and so right now this isn't what I would really need for you to do on this problem. I'd want you to do what I've already written. But just to practice this, go back and retype the cosine inverse of the 29.43 divided by 53.58 and get 56.6, and then all the digits your calculator has in it. And then you're going to store that into your memory. And for some of you, that memory is called by a letter like A, B, C. For some of you, that storage is called by a number like 1, 2, 3. And again, you're going to need to Google this and find out for your calculator how to do this. But I'm going to assume that you can store this under a letter. And so B. I'd use B as the place if that's the one I'm storing. So if it's numbers, I probably would use 2. So if it's letters A, B, C, and then for numbers 1, 2, 3. That way you get less confusion. Wait, where did I put that? And some of your calculators, actually, when you go to recall the number, you actually can see the numbers right next to the letters. So you see what was stored in each of your letters. And that's a good feature because you don't have to worry too much about trying to remember it on your own. So if we did this, we would have to find A. We would write that that's going to be the total of all 3 angles minus the 90 degrees minus, and then you're going to get the 56.68 number in there by recalling what's in B. Okay. Now, what I'm writing there is more what you would type than what I'd want you to write. I would actually want you to write in that spot the 56.68. But I would expect that you, since you're using a rounded number, that you wouldn't actually type minus 56.68, but you'd actually type minus and then pull back the answer with all the digits for B in there. And you should get, once you do that, the same answer when rounded to 4 significant digits. You should get this same thing. Okay? So everything I've written in green is not something I would necessarily ask that you do on this problem because you can avoid it. So everything in blue is what I really want you to do. This line right here to here is what you're typing, and what you're recording on paper is everything else that's not inside of the brackets. So that bracket stuff is kind of thought process or typing directions, if you will. Okay, so if we solve the entire triangle, do we know everything? Please be careful that you go back and look, because it's very easy to think, gosh, I've done a lot of work. I must be done by now. So look, you've got angle C, you've got angle A and angle B. So I've got all 3 angles. 2 of the sides were, oh, I didn't find B. That's unknown as well. So for a right triangle, how are the 3 sides related? See, I don't want to use one of my angles that I calculated to figure out what B is. I want to use only the givens. And the 3 sides of a right triangle are related to each other's lengths by the Pythagorean theorem, which says that the square of a leg of a right triangle plus the square of a leg of a right triangle equals the square of the hypotenuse of the triangle. And in this particular case, those letters are correct for this particular problem. But be wary, if I gave you a triangle labeled CAT, then the whole thing is different as to what your Pythagorean theorem will be. So it's more important that you know that leg squared plus leg squared equals hypotenuse squared than what some of you I know memorized was a squared plus b squared equals c squared. Well, that's true if the triangle is labeled as I've labeled it. Otherwise, you're maybe barking up the wrong tree. Oh wait, that would be a cat. Meowing up the wrong tree. Anyway, so into this formula, substitute in your givens, the length of A squared plus b squared, which we don't know, equals the square of C, which we were given. So I'll substitute that number in. So to get b squared by itself, you'll want to subtract. Oops. I know some of you are tempted to just go ahead and simplify those, but you're going to have a lot more digits to write than if you just leave it alone. So just saying. Now to solve for b, what will I do? Well, I'll take the square root of both sides. I'm not going to put in plus or minus in front of the radical because b is the length of a side, so we know that that's positive, so it's simply the square root of. Don't write plus or minus here because of the context of the problem. The side length must be a positive number. Okay, so this is now calculator ready. Type that in. And you might want to pause and type that in and make sure you get the right answer. I got 44.77 using 4 significant digits. And the units of measure for the sides is in centimeters. Okay, so another topic that is going to involve right triangles is if you are, let's say, standing on a cliff and you're looking down towards a boat. Sorry for my poor drawings. Very childlike, I know. If you're looking straight out, so parallel to the surface of the water, from the horizontal, in other words, if you look down at the boat, the angle that your eyes move to go down toward the boat is called the angle of depression. Not that hard of a concept to deal with, but I want you to be able to envision what it is they're talking about when they use a phrase like angle of depression. It's the angle down from the horizontal. Then another thing that can happen is that you're standing on the ground and you're looking up at a plane. I know, laugh all you want. My plane and all my drawings are just really bad. That's fine. It's not a big deal. So if you look up from the horizontal, the angle that your eyes move up to look up at that plane in this case is called the angle of elevation. As it turns out, both of these situations actually involve both ideas. The angle, if you were in the boat looking up, and this is your horizontal, then the angle of elevation would be that. And if you know anything about, from geometry still, about parallel lines, if you have parallel lines that are cut by a transversal, then the angles on opposite sides on the interior of the two parallel lines are congruent. And what that means is that in this picture, the angle of elevation from the person in the boat looking up at the person up on top of the cliff, that angle of elevation is congruent to the angle of depression. Okay, so that's kind of an important discovery. Is this geometry helps us. Sometimes they may change the orientation, and you need to figure out, well, if they talk about the angle of depression for the guy on the cliff, and then switch it to be the angle of elevation for the person in the boat, those are actually the same angles. And you could have a similar idea for the if there were a person in the plane looking down, that would be their angle of depression. And the opposite interior angles are congruent, and that's what you would use to explain those two ideas. All right, so anyway, those are a couple of phrases that you're going to encounter, and I wanted you to have a good understanding of them so that that would not limit your ability to do a problem. Okay, so when you're solving word problems, which is what the majority of this section is, I would say draw a sketch is one of your most important tasks, because once you have your sketch, you'll be reminded of things like the Pythagorean theorem, the relationship between angles and two sides, one of the trig relationships, sine or cosine or tangent. And on that drawing, label every quantity that you have been given and label every quantity that you're supposed to find with a variable. Then use your sketch to draw a conclusion about what kind of equation would be best that relates the given quantities to the variable you're trying to find. And third, solve the equation and double check that your answer makes sense. Like if you've mistyped something, maybe you expected a 30-degree answer or so, and you got 7 degrees. You may think, oh wait, what did I mistype? At least I hope that's what goes through your head. Okay, so let's do an example. The length of the shadow of a building, 34.09 meters tall. Okay, so as soon as they're talking about this, I'm going to draw a building. And an assumption we're always going to make is that all buildings are vertical and all ground surfaces are horizontal, which is not accurate really most of the time, but we're going to make that assumption. Let's see, the length of the shadow of a building that's 34.09 meters tall. So I need to label that. Height of that building is 34.09 meters. Okay. And it says that the length of the shadow is 37.62 meters. So assume that we have the sun over here casting rays, and most of the rays, when they hit the building, that's what creates the shadow. And then there's one first beam of light that grazes the top of the building, and that's where this light that's shining ends up being lighted here. So this is all lighted region, and that means everything over here is in shadow. So all of this is in shadow here to right there. And the length of that shadow, that is the distance from the base of the building to the tip of the shadow, is, according to them, 37.62 meters in length. Okay, well, as soon as I draw that, you see the right triangle, obviously. And so we can infer that this is a right angle. So we have a right triangle. And I've labeled the things that I know. Let's see what the question says. Find the elevation of the sun. Okay, the angle of elevation is going to be the angle of elevation from the ground up to the sun. So this angle right here. Okay, and we can call that angle J if you want to. Doesn't matter what you decide to call it. They didn't give it a name, so it's your choice what to call it. And now that we have a picture, what is the relationship amongst the two givens and the angle that we're supposed to find? Well, for angle J, the height of the building is opposite and the length of the shadow is adjacent. And what trig function relates an angle to opposite and adjacent? Well, cotangent's correct, but you don't want to use that one because this is going to be a calculator thing. So you really want to use sine or cosine or tangent on these problems, even if something else is appropriate, like cotangent could have been used. You're just making yourself a harder problem. So the tangent of angle J is opposite, 34.09, divided by adjacent, which is 37.62. All right, then to solve for angle J, we'll need to take the tangent inverse of that fraction, that ratio of two sides opposite over adjacent. This is a good place to pause and type this in and make sure you can get the right answer. And the answer I got was 42.0. You know what? I need to think about significant digits. The two givens have 4 each, so that means my answer should have 4. So 42.18. What are the units for angle J? Degrees. If you don't put a degree symbol on there, I assume you mean 42.18 radians, which is a very big angle. Will not fit inside of a triangle. So that's your answer to that one. Okay, so let's see what else we have here. Now, another concept that's used in navigation and orienteering and piloting, I suppose, which is navigation in the air. But anyway, there are a couple of different ways that are used, different systems, if you will, for measuring your bearing. One of them is angle from due north. So we'll always have a due north as our initial side, and this is different from our normal angles in that initial side is north instead of the positive x-axis. And the other thing that's different here is that the terminal side, when you draw it, let's say it's right there, you're measuring from north clockwise instead of counterclockwise. So this might be like 68 degrees or something. Okay? And so if you say that the bearing is 68 degrees, that's a picture of it right there. So if I give you a bearing and it's a single number in degrees, then you're going to go from due north clockwise that far. And so you can have all kinds of things, and the answer has to be between 0 and 360. So you might get to like right here and have this angle from due north that is perhaps, I don't know, just make up something, 350 degrees or something, right? And again, that's always measuring from due north. So this would be a bearing of 350 degrees. Okay. So let's do a problem that involves that way of that system of calculating the bearing, and make sure that we know how to use that properly. Okay, so let's look at the next problem. Radar stations A and B are on an east-west line with A west of B. Okay, so here's A, and that's west of B. So this is my east-west line, and A is west of B. All right. And the distance between them is given to be 3.70 kilometers. Okay. Looks like we have 3 significant digits so far. Station A detects a plane at C on a bearing of 61 degrees. Okay, so what I'm going to do is I'm going to draw in a due north from A, and I'm going to rotate it. They said 61 degrees. I'm going to go from there clockwise about 61 degrees. Now, of course, I don't know that this is accurate. That's perfectly 61 degrees, I'm guessing. And the accuracy of my drawing is not what's really in question. It's just, do I have the right idea? So from the information given, I just know that that plane is somewhere on this ray. Okay, so that doesn't locate it quite, but I know looking from A, it's going to be somewhere along that pink line. All right, now keep reading. Station B simultaneously detects the same plane on a bearing of 331 degrees. Okay, so let me draw due north for this guy. And I want to go 331 degrees. Let's see, if I go to here, it's 90, 180, 270, and how much more? 270, so that'd be another 61 degrees, right? So about like that. So that's 331.0 degrees. By the way, that has 4 significant digits. Otherwise, I've seen 3. And so we're going to take the least precise of those. We'll take, our answers need to be in terms of 3 significant digits, if that's the system we're using for rounding. Okay? All right, so then what do they ask us to find? They say, find the distance from A to C. Okay, they said the plane was at C, and I never labeled that. So it's, where is it going to be? Well, if the person looking at it from B means it's on this yellow ray, and the person looking at it from A means it's on the pink ray, seems like that means that point C is right there. One of the things I said as I was graphing that was I got to 270 when I got to the blue line here, the east-west line, and I said, how much further do I have to go? And I figured 61 degrees. That's something I said at the time, and that's kind of important that we get that right. And that was actually a pretty bad pun, sorry. You'll see why in a second. Do I know that I have a right triangle? It wasn't given. It didn't say that the 2 sight lines were perpendicular to each other. So we can't assume that. We're going to have to calculate that. So looking at the triangle that's created, the ABC triangle, what is this angle measure? Well, since due north and east-west are perpendicular to each other, the angle at A is the complement of 61 degrees. So A is going to be 90 minus 61 degrees, which is 29 degrees. So this is a 29-degree angle. So what does that make C? Well, C, since the triangle always adds up to 180 for the 3 angles, C has to be 180 minus 61 and minus 29, and that is 90 degrees after all. Of course, they didn't say I had to solve the whole triangle, but I do have to make sure that I'm in a right triangle situation before I can make assumptions about what I can and cannot use. Okay, so let me read the question again. Find the distance from A to C. Well, since I've labeled that angle down for the triangle B, I'm going to call the side across from it, I'm going to call the side across from it B. So let's say this is B right here, and it's B that I'm supposed to find. So I actually had to calculate both B and C. So it doesn't really matter which one I use. 61 was actually a given, so I'm tempted to use that one. So look at angle C, angle B, I'm sorry, angle B, which is a given number. 61.0 degrees actually. I rounded it when I wrote it in the triangle. And I'm given side AB, and I'm supposed to find side B, which is the distance from A to C. So what will I call side B relative to angle A? Well, it's opposite. And what is the length 3.70? That's hypotenuse. So what trig function relates opposite to hypotenuse? It's sine. So that means that the sine of the angle we've chosen to use, I'm going to put it back with the 3 significant digits it started with, the sine of that angle is opposite B over hypotenuse 3.70. So to solve for B, I'm going to multiply both sides by 3.70. It's now in calculator ready form, so pause and type this in and make sure you get the right answer. Okay, so what did you get? I got, with 3 significant digits, I got 3.24. And what is B measured in? Kilometers, right? So don't forget the units are kilometers. You need to write that down. Okay, so that's one problem that we might have to do with bearing. If we're using bearing, it's a single angle in degrees between 0 and 360. Okay, so that's the first type. The second type of measurement of bearing is you start with a north-south line. Okay, and then your angle is closer to one of those than the other. So for example, the angle I draw right here, that's closer to north. And let's say that it's 22 degrees away from north. Then the way that you'd express that angle is that you're starting out close to north, so you write north, and you're moving 22 degrees from north. Which direction? Towards the west or the east? This is towards the east, because this is east, this is west. And so the way that we name this is either north or south first, the acute angle from north or south, and then which way did you move from north or south to get there? Did you move in an easterly direction or a westerly direction? So let's just look at some more examples of these. The 4 that they have, we'll just do them. So if this is due north and we move 42 degrees, not drawn to scale, of course, what will we name this? From north, we're going 42 degrees in an easterly direction. Okay. What about this one? There's due south, and let's say this is 31 degrees. What would we name this one? From due south, we're going 31 degrees east of due south. Okay, let's try another one. This is due south. This is, say, 40 degrees. How would you name this one? We're starting at south, and you're moving 40 degrees. And which way from due south are you moving? West of south. Okay, and then the last example they give us looks something like this. How would you name this bearing? It is from due north, we're moving 52 degrees in what direction? To the west of north, correct. So the first letter is either N or S, then there's a degree measure that's acute, And then the second letter after the number is either east or west. It's either E or W. And that's how this system of measuring bearing is done. Okay, so now that you have that idea firmly in your grasp, let's do a problem. The bearing from A to C is south 52 degrees east. Okay, so let me say A is right here, and the measurement is from A to C is 52 degrees easterly. Okay, so here's due south, and I'm going to move how far? 52 degrees east of south. So again, I'm going to sort of estimate in my drawing just how big 52 degrees is, and C is somewhere along that line. Okay, I'll go ahead and put it right here and hope that I can make this look right. Okay, then the bearing from A to B is north, so from A we've got to move north. From north, we're going to move 84 degrees east. So 84, gosh, that's almost 90. So this is almost 90. Obviously not drawn to scale, but just so it sort of looks right. Okay, so that's 84 degrees. And I don't know, it's going to be somewhere out here. Let's just say it's right there. I think that's good enough. Okay, then the bearing from B to C is south. Okay, so I need a southerly line. Due south. Going from south, I'm going to move 38 degrees west. Okay, so that's supposed to take me to C, and that is 38 degrees by declaration, not by accurate drawing. Okay, just saying that's probably not super duper accurate. If you were to draw it to scale, it would probably look a lot different from what I just did. Okay, so let's see. What can we discern from this? Well, the angle, so you see the triangle, right? ABC. The angle at A that's inside the triangle, I think I can figure that out because the total of all three angles, the green one and the white one, and I guess I'll mark this with blue, and this angle have to add up to how much? Well, 180, right, because that makes a line, and a straight angle is 180 degrees. So A will be the 180 for the line minus the two measures that we know are part of that line's angle, A being the other part, and A is 44 degrees. So any angle inside the triangle you can find is a good plan. Okay, now what? Let's see. I'm going to extend this line upward a little bit. I didn't need north from B, but I'm going to draw it anyway. And the reason I did it was because the two north-south lines are parallel to each other. And one of the things, and I didn't say this yet, I sort of alluded to it earlier, but whenever you have parallel lines that are cut by a transversal, I already mentioned that alternate interior angles are congruent, right? Well, one other thing that you could say is that whatever this angle is, it has to be the supplement of the marked in gray angle, and alternate interior angles are congruent. And so what that means is that the one marked in gray right here and the one marked in green right here are what we call same side interior angles. And what are they to each other? They're supplements. Right, they're supplementary. So that means, therefore, that the angle right here is the supplement of that 84. So that angle will be 180 degrees minus 84 degrees, and so that is 96 degrees. So that's a 96 degree angle. Why did I care about that? Well, I care about that because I can now find the measure of angle B, the one that's interior to the triangle. And again, we have a straight angle. 96 are unknown, and 38 have to make 180 degrees the straight angle there. So let's find out what that is. Angle B will be 180, the total of the line, straight angle, minus the 96 that we now know, and minus the 38 that we figured earlier from our reading of the problem. And that means that B is 46 degrees. So this is 46 degrees. So my thought process here was to try to see if we could figure out what kind of triangle we have, which meant I needed to know those angles. And so what should angle C measure? Angle C, since I know two of the angles are 44 and 46, the sum of all three angles in that triangle is 180. So if I subtract the 46 degrees and the 44 degrees, I end up getting 90 degrees. So that's actually a right angle. And instead of drawing an arc, you could draw that little box in the corner, meaning it's a right angle. Or you could leave it as an arc with 3 marks on it. Either way. Anyway, that's a right angle. So that means we're in a right triangle situation. Okay. So, that's a lot of information. And we still haven't even read the whole problem. So a plane flying at 250 miles per hour. Okay, so 250 miles per hour is the speed of the plane. Takes 2.4 hours. Takes 2.4 hours to go from A to B. So how would I find the distance that the plane traveled from A to B? Well, if you notice the way I've set it up, if you multiply these in using dimensional analysis, you'll find the length from A to B, which I'm going to call C, little c. And the length of C is the length in miles. So 250 miles per hour for 2.4 hours, you multiply those, and you get 600 miles. So this is now known to be 600 miles. Okay, now the question is, what is the distance from A to C? What's the distance from A to C? Which I'm going to call B. What is the distance from A to C? Well, since we have a right triangle, and C is obviously the hypotenuse, depending on whether we want to use A or B, both of which we calculated. Remember earlier I said sometimes you can't help it, and you have to use a calculated value. This one isn't rounded, so it scares me less than using a rounded answer to go forward. These are all exact for the angles, so I don't really care which one we use. Let's use A. So if we use angle A, how is angle A related to C, the hypotenuse, and B, which would be its adjacent? Well, that's cosine, right? So the cosine of angle A should be adjacent, which is unknown B, over hypotenuse, which is 600, which 2 is a calculated value. Oh, wait, I know what A is. Why did I write the letter A? That was silly of me. I mean, it's not false. It's just not what I should have written. What is the measure of A? What should I have put there? A is 44 degrees, right? So to solve for B, I would multiply both sides by 600. That's in calculator ready form now. And B is approximately 430 miles. And again, I think they're using significant digits. And the 52, the 84, the 2.4, all of those were 2 significant digits. So I'm going to round this to 430 with 2 significant digits. And the units are in miles. Okay. So that's that one. All right. Let's do another problem. Suppose that at takeoff you notice that the runway is labeled 12L, but you miss what the corresponding R number is. The pilot turns right onto the runway. What would the R number on the sign be? Explain your reasoning. Well, first of all, we have to kind of understand what they're talking about. If they say 12L, what that means is that it's 120 degrees left. So these are going to be multiples of 10 angles, 120 degrees. If you divide that by 10, you get 12. So that's what the 12L stands for, is you're 120 degrees left. So as you're on the runway for takeoff, you see that this is your runway, and it's labeled 12L. Oops. Well, I guess that's close enough. So this runway is labeled 12L. Trying to decide where to write that. And so you're going to turn onto the runway. So you're on another road, if you will. And first of all, let's make sure we understand why it's 12L. So it's 120 degrees is the bearing. So if I were to measure from due north, my supposition is that should be 120 degrees. I don't know that it's drawn to scale. That's why I was kind of hesitating with my statements, because that's kind of close, I suppose. All right, so it's like this runway is labeled 12L, and what follows that is a number followed by R. And you missed it. You missed what that R number was. And so what would that be? Because you need to know what the right one is, because you're turning right onto it. So what would the corresponding R number be for that? Well, the right bearing is the opposite direction from the left bearing. So if this is 120 degrees left and I wanted to go the opposite direction, that would be like saying from here, if this is due north, what number is that? Okay, does that make sense? What number is that? So how would you get that? Well, let's see. If I drew them together, maybe that would help. So here's the 12, so 120 degrees. And here's the R number. And what is that? Well, how far is it from the green around to the pink? Just this part of it right here. How far is that? Well, that's 180 degrees, right? So, so if that's 180 degrees, and let's say that we're going the pink one. The pink is partly the green and partly the purple. So isn't green plus purple going to be the pink? And that's going to be 300 degrees. Does that make sense to you? The original part, starting from due north, is where we're going to start. And getting from the due north to the green line is 120 degrees. Then you go 180 from that to go the other direction to get to the pink. So you add 180 to 120, and that's 300 degrees. So this one is 300 degrees. Okay? So because of that, that means that this number 300 divided by 10 means that the right number is 30. Because you always divide the degree by 10 to get the L or the R number. And that is a good indicator of what we're going to do. Because they're opposite directions, they'll always be 180 degrees away from each other. So the L number and the R number are always 18 away from each other, because they're always going to be opposite directions. So they'll be 180 degrees away from each other. And that's going to be an R or L number of 18 is a difference. So the R number would be 30. And the second question is, what direction is the plane headed at takeoff? Well, its bearing is 300 degrees. So the bearing is 300 degrees at takeoff, which is roughly, how would you describe that? This direction. What would you describe that? It's roughly northwest, right? If you wanted to put it into layman language. Roughly northwest. It's headed northwest when it takes off. Alrighty. Okay, calculating the distance to a star. Let's see what this is. Okay, so in 1838, Friedrich Bessel determined the distance to a star called 61 Cygni using a parallax method that relied on the measurement of a very, very, very small angle. You observe parallax, just to explain what it is, when you ride in a car and see a nearby object apparently seems to move backward with respect to more distant objects. I don't know if you've thought about that, but if you're driving along and you look at something close, and you can see something in the distance, the thing that's close will appear to be going backwards with respect to things that are far away. So, as the Earth revolved around the Sun, the observed parallax of 61 Cygni is theta equals 0.0000811 degrees. Very, very, very small angle. And so when you do this, let's say we have some unknown star here up in the sky, and we have the Sun, our Sun, right here, and the Earth of orbit, and this is way out of scale, okay? But just kind of go with it for a second. If this is Earth, also not drawn to scale, right there, then if you were to draw in the Earth to Sun distance, and then from the Sun to that star, and then the length between the Earth and that star, which is what we're interested in, that's going to be that little bitty angle is that theta right there, which of course I've drawn way out of scale because the star is going to be a lot further away, which makes the angle very, very, very small, but drawn out of scale so that you can see it. And the distance between Earth and the star is the length of this pink line. Okay? So, now that that's been set up, let's answer a question. One of the nearest stars is Alpha Centauri, which has a parallax of theta is approximately 0.000212 degrees. First, calculate the distance to Alpha Centauri if the Earth-Sun distance is 93 million miles. So the Earth to Sun distance is 93 million miles. Okay? All right, so since the Earth to Sun and Sun to Star distances are perpendicular, we're going to assume that we have a right triangle and that the distance that we're trying to find, d, and the angle that was given and the distance between the Earth and the Sun is given, that those three measurements are related to each other. So according to angle theta, what would we call the distance from Earth to Sun? Opposite. And the distance from Earth to star, that's the hypotenuse. So what trig function relates opposite and hypotenuse to the angle? That's the sine, right? So the sine of our very, very small angle, make sure you're in degree mode, by the way, the sine of that angle is going to be opposite 93 million divided by hypotenuse, which is d. So I'm going to use that trick I showed you where if I have a fraction equals a number and the thing that I don't know is in the denominator of that fraction, the number by itself and that variable can just switch places. I like that shortcut and I really like to use it. If you need to cross multiply and divide to get that, you're welcome to. I just think this trick is handy because we're going to be doing it or needing to solve something like this setup often enough where knowing how to get from the first green line to this one quickly is a nice thing. So type that in your calculator and see what you get. You might notice that we were given 212. So I'm going to use 3 significant digits, even though the 93 million only has 2. I want to use 3 in this. No, actually, I want to end up using 2. But we're going to need to use this, go ahead and round to three numbers, three significant digits for this, please. And you should see 2.51, and then maybe some funny symbol that means that you're in scientific notation. And the way to write scientific notation correctly on paper, it may not match what your calculator shows, but on paper it should be the 2.51, the old times, the x for times. That's not a variable x, that's multiplication. It's one of the last places where we still write x for multiplication. We really don't use that for multiplication normally, except in scientific notation. Times 10 to the 13th. And of course your calculator went to scientific notation because this number was so big. And that's one of the uses of scientific notation, is to make a really far away from zero number look manageable. And of course that's in miles. So 2.51 times 10 to the 13th miles. Now if you read B, we're going to then convert that to light years. So keep that number in your calculator. Keep it handy because you're going to need it again. Do not retype the 2.51 times 10 to the 13th, please. Keep all of the digits. So store this in your calculator so you can use it again. So the part B says a light year is defined to be the distance that light travels in 1 year and equals about, so 1 light year equals about 5.9 trillion miles. So, can you write that in scientific notation, that 5.9 trillion? Try that. Okay, what you should have written is 5.9 times 10 to the 12th. That's what that is. Okay, so miles. So what we want to do is we want to take our distance d, which is still in the calculator, which is in miles, and I'm going to multiply it by 1 in the form of something that has miles in the denominator so that they cancel, and has light years in the numerator to become the new unit of my answer. So how many light years equal how many miles? Well, from the statement that we read earlier, 1 light year is equal to 5.9 times 10 to the 12th. Type this in your calculator and see what you get. And when you're done, round to two significant digits. You should have gotten 4.3 light years. If that's not what you got, please talk to me, and we need to talk about how to type this in your calculator correctly. If you can't get that, well, I'll just give it away really fast. In your calculator, if you type 2 times 3 divided by 6 times 4, what's it going to do? Well, it's going to do those operations from left to right. So it's going to do 2 times 3 is 6. Then 6 divided by 6 is 1. And 1 times 4 is 4, right? But what if this 2 times 3 is kind of like scientific notation? That's a number in scientific notation. Well, that's not, but pretend. And then this is a number in scientific notation. So what would that be? 2 times 3 is 6, divided by 6 times 4 is 24. 6 divided by 24 is 1/4. Those are not the same. So let me caution you that if you want this to be correct, when you do that division, you're going to want to put parentheses to protect that the times 10 to the 12th is part of what you're dividing by. It's not what you're multiplying by. It's 5.9 that's multiplied by 10 to the 12th. So if you didn't get the correct answer, try taking your answer from part D that I hope you stored in your calculator and divide by left parenthesis 5.9 times 10 to the 12th, right parenthesis, enter, and see if you get the correct answer that way. And you're going to have to be aware of that when you're doing things with your calculator. It's just one of those things that you got to know if you want the right answer. Okay, so let's see. Let's go here and look at another problem. Francisco needs to know the height of a tree. Okay, so I have a tree here. Again, my drawing abilities are infantile, so don't castigate me too much. He needs to know the height. So the height is, of course, this measure from the ground up to the top of the tree. From a given point on the ground, so some point on the ground, let's say this point right here, he finds that the angle of elevation from that point on the ground to the top of the tree is 36.7 degrees. So from here to the top of the tree is 36.7 degrees. Okay? And let's see, he then moves back 50 feet. So he started at the pink dot. He moves backwards 50 feet from the pink dot to get to here. And from the second point, the angle of elevation is 22.2 degrees. That's 22.2 degrees. Okay. So we've drawn, I can't even talk, we've drawn a pretty good picture of this, and we're supposed to find the height of the tree. We're supposed to find h. All right, so, well, they didn't tell us how far from the tree to the first place was. So since that's an unknown, I'm going to call that distance x. And if I use that and the height of the tree here, that's actually a right triangle. And this side down here is x. So for the pink triangle, what I'm thinking of doing is trying to find a relationship between the h that I'm trying to find, the given 36.7 degree, and the x that I introduced, something they didn't tell me about, but I think I need to know it. So what is that relationship? Well, from 36.7 degrees, h is opposite and x is adjacent. So that means that the cosine of 36.7 degrees, what am I saying? Not cosine. Opposite and adjacent. What relates those two? Yes, it's tangent. I think I may have said tangent, but anyway, no matter what I said, it's supposed to be tangent. Wow. Having one of those days. So the tangent of that angle is opposite h over adjacent x. Well, unfortunately, with those three things, you have to know two of them to find the third one. So I don't know what x is, so I can't figure out h, at least not yet. Well, that's why they gave me this other point. So is there a right triangle I could draw using the 22.2 degrees? Well, the adjacent side for it is how long? And this is the tricky part. Yeah, it's x plus 50 away from the base of the tree. So let's write a true relationship using 22.2 degrees, the x plus 50, which is adjacent, and h, which is the opposite. And again, the relationship is that the tangent of 22.2 degrees is opposite h over adjacent x plus 50. Well, in reality, what we've created is a system of equations, two equations with two unknowns. So we're going to have to use one of our solving techniques from college algebra for solving a system. And I think the best one here is going to be to use substitution. I'm going to take that first equation and solve it for h by multiplying both sides by x. And I know that these heights of the tree in these two equations have to be the same. So that means that I could take that h that I just solved for and the other equation, and wherever the h is, take it out and substitute for it with what I just calculated h to be, x tangent of 36.7 degrees. And that'll be over x plus 50. So now I only have one equation that has one variable x in it, so I should be able to solve this for x. So to solve this for x, I'm going to start by multiplying both sides by x plus 50. Which gives me this equation. I have x in two places. So kind of remember back to when problems that you had in earlier courses, like if you had x plus 1 times 7 equals x times 4. This kind of looks like that one, is why I tried to make it up to look kind of like that, but these are easier. Wouldn't you, if you have x in two places, distribute the 7 first? Right? And then wouldn't you perhaps then subtract 4x from both sides and subtract 7 from both sides to get all the x's on the left together so that you could collect like terms? Anything that doesn't have an x on it, put it on the other side, that negative 7, and after you collect like terms, you'll divide by 3, right? Does that seem like it makes sense? So that's the basic process algebraically that we're going to do. Just over here it looks nastier. So I'm going to distribute the tangent of 22 degrees, so that will be x times tangent of 22.2 degrees plus 50 times tangent of 22.2 degrees equals x tangent of 36.7 degrees. Then I'm going to get all the x things on one side. So the x tangent of 22.2 degrees is already there, so I'm going to leave it alone. Minus the x times tangent of 36.7 degrees. And the 50 tangent of 22.2 degrees doesn't have an x on it, so I'm going to subtract it from both sides to move it over to the other side. See how this parallels what we did over there to the left. Now the one thing that you're so used to doing, this collecting of like terms of 7x minus 4x that we talked about, in reality, let me slow you down on that, what you've done is you've factored out an x, leaving inside 7 minus 4, and then you combined 7 minus 4 to 3 to get the 3x. So that's what we're going to do over here, is we're going to factor out that x, which makes it an equation that has only a single x in it, which makes it something for which we can solve. We can't really combine like terms there. Those are just subtracted things that we're going to have to put in our calculator to do the subtraction. But anyway, to solve for x, we would divide both sides by that difference. Tangent of 22.2 degrees minus tangent of 36.7 degrees. Okay, it's probably the most complicated thing I've asked you to type, so please pause the recording, type that in, and see if you get the right answer. Actually, I don't care if you get the right answer for that or not, because that's not what we're looking for. I just thought about that. We were solving for the height of the tree. It doesn't really matter what x is. Although we did need to find x to solve the problem. That's not our last thing. So even though that's in calculator ready form, I really don't care what it equals per se. But if you've already typed it, there's nothing wrong with that. You'll still use it. So how do I solve for h? Well, if you look up at the top of this work, to solve for h, the best equation that will give you h once you know what x is that one. So I'm going to use the value of x we just found, which you may have already typed into your calculator, which is fine. It'll take me a minute to write this. So what I'm writing is the calculator ready form. And that's what x is times the tangent of 36.7 degrees. And rounding that to 2 significant digits, you should get that that's about 45 feet. Again, that's complicated, so if you can't type that in, ask for help in class, and I'll be happy to go over that with you. All right, that ends the lesson for today. I will see you in class.